Hello and welcome back to the course. So today we're going to look at higher order linear ODEs. So linear ODEs of order 3, 4, 5, and so on. And so this is section 2.3 in the book. You can get the book at its URL or click on it in the description. You can browse it on the web. You can get a PDF or you can buy a paperback if you want. All right. So what are we doing? Let's consider linear equations of order higher than 2. Right? And the idea is mostly the same. It's just we're going to have more linear independent solutions. We're going to have more initial conditions and so on. But otherwise, the idea is basically the same. So start with superposition, which is, again, is the same. Suppose that I have a homogeneous linear equation of order n, right? So this goes up to the nth derivative, right? And I have n solutions, y1, y2, y3, all the way up to yn, right? So if n is 4, I have y1, y2, y3, y4, right? And suppose that they're all solutions of this equation. That means if I plug them into here, they satisfy the equation, right? So then, if I take a linear combination, meaning I look at an expression like this, where the C1 through Cn, so C1, C2, and so on, are all constants, and they can be arbitrary constants, then this linear combination is again a solution to this equation, right? So if I have a whole bunch of solutions, I can create more and more solutions out of it, right? By including these constants. And the way it will work is basically, going to try to figure out, once you have sufficiently many solutions, meaning sort of n sufficiently different ones, and this is going to be, again, linear independence, but it's a little bit more complicated. We're going to talk about it in a little bit. Once you have enough of these solutions, then you write down this solution and you have n arbitrary constants, and you're going to, for an nth order differential equation, you're going to need n initial conditions, and that's going to allow you to solve for these constants, right? So basically the same idea, just with more, right? But it's we're doing the same thing. All right. Now we also have existence and uniqueness in higher order. So suppose I have this linear equation. Now, we can allow a right-hand side as well. It doesn't have to be homogeneous. So suppose that on some interval, I'm going to call the interval I, these functions are all continuous, right? And suppose that I have some constants b0, b1 through bn minus 1, right? Then this equation, maybe get rid of all of just so it doesn't become all yellow. Then this equation has exactly one solution that satisfies these initial condition, and actually the solution is defined on the entire interval I, right? So for linear equations, we're never going to get something, something that blows up in some, after some, small amount of time. It's always going to exist wherever the equation is nice, and you're going to get a unique solution given sufficiently many initial conditions. So the function value, the first derivative, all the way up to n minus 1, n minus first derivative, right? So if I give all of those, it guarantees a unique solution to this, right? All right. So let's talk about this linear independence, right? So to be able to use this superposition, right, and to really get sort of different solutions out of it, enough different solutions out of it. Well, we need to start with enough linearly independent solutions. So now it's slightly different, but it's again still that we can solve for one in terms of the others, but it's easier to write it down in this way. So we'll say that y1, y2 through yn, these are linearly independent, so it's a linearly independent set of functions. If this equation, where I take a linear combination of them, that means I take a constant c1 times y1 plus a constant c2 times y2, all the way up to, plus a constant times yn. If that equals to 0, then the only solution is this trivial one, meaning all the c's are 0. I mean, that's clearly a solution here, right? But they're linearly independent if that's the only way that you can solve this. So this has to be true for all x, for example, right? Because y1 through yn are functions of x, right? So now if there is, if you can find a different solution, right? Let's suppose that c1 is non-zero. Then, well, I could just divide by c1, right? I divide both sides of that equation by c1, and then I could solve for y1, right? So I could solve for y1 as a linear combination of the others, right? So really, y1 is not adding anything to my set of solutions, right? Because I can already get it by a linear combination of the others. So that's really why I'm interested in linearly independent solution. I want each one to add something, to bring something new, right? So if I have one that is a linear combination of the others, it's not really, adding anything. So if the functions are not linearly independent, they're linearly dependent, just like before, right? So again, it's basically the same thing. So before it was that the one function was a constant multiple of the other. Well, it's the same thing here. It's but instead of just a constant multiple, I have to take a linear combination, right? And it doesn't have to be, of course, it doesn't have to be C1. It could be maybe C1 has to be 0, but maybe C2 is not 0, right? So maybe I could solve for solve for Y2 in terms of the others. Okay. So let's go through an example. Let's go see that these three functions, e to the x, e to the 2x, and e to the 3x, are linearly independent, right? Let's understand what this means on this example, right? So, all right, so consider this basically this equation, but with these three functions, right? So I write down this equation. I'm trying to solve it, right? I want to, figure out what is the solution, basically what are all the solutions, C1, C2, C3, and I want to show that it's, zeros is the only way that I can solve this. I mean, clearly that's a solution, right? If I multiply all these by zeros, yeah, that's a solution. I want to know, is there any other one, right? So here, and we're going to do a bunch of, I think 3 different ways of doing this. So let's start with one. Well, in this case, I could look at, let's suppose that I write e to the x, I write it as z, right? Some number z. And then I notice that z squared, just by the laws of exponents, it's e to the 2x. And e to the 3x is z cubed, right? So this equation is really this equation, this polynomial, in terms of z, in this sort of this number z, right? Now, this polynomial has to be just 0 for whenever z is anything that you can write as e to the x, which is any positive number, right? So if this polynomial is 0 for any positive number, it has to be the 0 polynomial. That is the only way that this can work. And so the polynomial is identical to 0. That means that its coefficients are 0, right? So therefore, the only solution here is C1 is equal to C2 is equal to C3, and that's 0, right? So the functions are linearly independent. Let's see another way of showing this for these guys, because there's always a whole bunch of different sort of ad hoc ways that you can do this for any specific functions. So let's start again with this equation, and let's divide by e to the 3x. If I divide by e to the 3x, you will notice that over here, the e to the x, if I divide by e to the 3x, I'm going to get e to the minus 2x, right? Dividing by e to the 3x is like multiplying by e to the minus 3x, right? Anyway, so I have e to the minus 2x, e to the minus x, and then, just 1 here, right? So it just becomes C3. Now, this is supposed to be true for all x, right? So if it's true for all x, what I could do is I could take a limit as, let's say, x goes to infinity, right? Now, as x goes to infinity, e to the minus 2x goes to 0, right? Because it's exponential decay, right? It goes down towards 0. E to the minus x goes down towards 0. So if I let x go to infinity, then this will go to 0 and this will go to 0. And I'm going to be left with C3 equals 0, right? So C3 has to be 0, right? For this to be true for all x means this is true for all x, meaning C3 has to be 0. So what I'm left with is, well, C3 is 0, so I'm left with this equation. And I could just, repeat the same argument. I could divide by e to the 2x, right? I would get C1 e to the minus x plus C2, and let x go to infinity, and that would give me that C2 is going to be 0. And once C2 is 0, then I would just have, my equation would be just C1 times e to the x is 0, and if you divide by e to the x, you just get C1 is equal to 0, right? So they all have to be 0. The functions are linearly independent. Okay, let's do a third way, right? So suppose that, again, I'm starting with the same exact thing. Now, this way will always work, but it's maybe a little bit annoying to do. But if you suspect that you have linearly independent functions, what you could do is start plugging in different x's, right? Because if this is true for all x's, well, it's in particular true for whatever x you plug in, right? So, for example, here, I could plug in x equals 0, I could plug in x equals 1, I could plug in x equals 2. And I'd get 3 equations where there's no x anymore, but it's going to be 3 linear equations in the C1, C2, and C3. What I get is this thing, that's when I plug in x equals 0. I get this guy, that's when I'm plugging in x equals 1. And I get this guy, that's when I'm plugging in x equals 2. Right? And so I have 3 equations, 3 unknowns, and this is just a little bit of algebra. And if you solve these, again, you have to do some algebra. So let's skip the exact details, but you're going to find out that C1 is equal to C2 is equal to C3, which is 0. So the functions are linearly independent, which we already knew, but so this is just 3 different ways of seeing it. And again, this last way, that should work basically for any functions. Now the idea is that you'd probably want to pick the x's in a nice way so that you get easy to solve equations, right? I probably wouldn't want to do like pi and 20 and 3 million over here. 0, 1, and 2 would work. Maybe 0, 1, and minus 1 would be another good choice, right? Just big, simple ones. Namely, x equals 0 is the really simple one, because then I just get, e to the whatever times x is just going to be 1. Now, there is, there's a certain thing called the Wronskian, which is basically just start taking derivatives of this function and you form a matrix. And anyway, let's skip what you do there. It's sort of a procedure. If you understand what linear independence is, and you have enough linear algebra background, you could figure out why this works. But otherwise, it's just this procedure that can tell you it is or it isn't. But it's not really, being able to by hand, check if a bunch of functions is linearly independent or not. That's not really that important. What is important is to understand what does it mean, right? So if you understand the meaning of it, being able to sort of run some procedure with the crank, well, who cares? You can have the computer do it. The computer can do exactly. Will probably if you have some sort of a symbolic computational program, We're gonna do the Wronskian in the background if it can check for linear independence. So the main point is to understand what it means, right? So don't worry about uh, having some complicated procedure, right? And the thing is that most of the time, when it's coming up, it's really you're getting some functions out of some procedure that you probably know are linearly independent as long as you're sort of doing the procedure correctly. So again, the main point is, what does it mean for linear independence? What does that mean, right? And it means that you cannot solve for one of the functions in terms of the others as a linear combination of the others, right? So I mean, here we know that we need linear independence, but the idea is that you also want to know when you would want to apply it in some other problem. When would linear independence be useful, right? And not necessarily knowing how to solve for how to figure out if some set of functions is linearly independent without understanding the technique. You can just use a computer for that if you don't want to understand it. All right. So let's have an example of linearly dependent functions. So for example, e to the x, e to the minus x, and the hyperbolic cosine of x. Now, they look different, but that doesn't mean that they're linearly independent. And what happens here is that the hyperbolic cosine is really, by definition, it is a linear combination of e to the x and e to the minus x. So therefore, it cannot be linearly independent. So if I have this, I could also maybe move everything to the right hand side and maybe multiply it by 2 to make it look simpler. And I have this linear combination, right? So C1 over here would be 2, C2 minus 1, C3 C3 would be minus 1 again, right? All right. So now you must consider all the functions at once, right? You cannot just consider some subset because, for example, over here, e to the x and e to the minus x, those are linearly independent. Actually, if you consider, any two of these, so either e to the x times e to the minus x, or maybe e to the x and hyperbolic cosine of x, or maybe e to the minus x and the hyperbolic cosine of x, all those, tuples, pairs of functions are going to be linearly independent. It's the set of 3 guys all together that are linearly dependent. And you can see that for the hyperbolic cosine, I need both of the other ones, right? I cannot just get it. It's not just a multiple of one of the other ones, right? It is actually this linear combination of the 2 other ones. All right, now, how do we solve an ODE? Well, a homogeneous equation like this. We try somehow. You have to run some procedure and somehow figure out n linearly independent solutions. And once we find n linearly independent solutions, then we write a linear combination of them, and that is the general solution. That's the idea, right? Because now you're going to have enough equations to be able to solve, right? Enough constants for which you can solve using the initial conditions. All right. So let's see an example. Let's suppose that we look at this equation over here, right? And let's put in some initial conditions. So again, it's the third order equation. So we have 3 conditions. We have the value of the function, the first derivative, and the second derivative at some point. In this case, 0. All right. So again, just like for second order equations, we plug in e to the rx, right? And so we plug that into this equation, right? So this is the third derivative, this is the second derivative, this is the first derivative. This is just the function itself. We plug that in just like before. We can now divide by e to the rx, and we get this the characteristic equation, right? So the characteristic polynomial of this equation, right, in R. And now we need to solve for R, right? Find the roots of this polynomial, right? And by trial and error, I'll say a little bit more about that in a little bit. Maybe we find that the R's that solve this are -1, 1, and 3. So the solutions are e to the minus x, e to the x, and e to the 3x, right? So now these are going to be linearly independent. So the general solution is going to be of this form, right? So now we have three, three constants, right? And we want to solve for them in terms of these three equations, right? So, well, so what do the initial conditions say? Well, first one, this condition, I can just write it like this, right? One is, well, if I just plug in 0 over here. The second, well, you have to take the first derivative that's going to, put out a minus sign over here and put out a 3 out here, right? So I'm going to get this has to be equal to 2, right? And the same thing for the second derivative, right? Then I'm going to get, minus minus is plus 1, so I'm just going to get C1 over here. And then over here, it's this 9 is the 3 squared, right? And now you just have to do a bunch of algebra again, right? So you have to solve this equation, and this equation. Maybe you could, there's some sort of obvious ways of doing it. If you like add the first two, you get rid of C1, right? And you're gonna get an equation in C2 and C3. And you could also do the same thing for the second and the third, and you're gonna get, again, C1 is gonna disappear, and you're gonna get another equation for C2 and C3, and you solve those two equations in two unknowns. And that you could do by maybe solving for C2 and plugging it into, in one of those equations and plugging it into the other one, right? However you want to do it, this is the result, right? C1 is minus a quarter, C2 is 1, and C3 is a quarter. And so the particular solution, right, the one that solves this initial value problem is precisely your minus a quarter times e to the minus x plus e to the x plus a quarter times e to the 3x. And, again, you could check that this really satisfies these initial conditions. That's easy, right? And I plug in 0, I'm going to get a quarter plus 1, minus a quarter plus 1 plus a quarter. Yeah, that's 1. With the derivative, there's going to be a minus sign, so you're going to get a quarter out here, still just 1, and over here you're going to get a 3 coming out, right? So it's going to be a quarter plus 1 plus 3 quarters, and that is 2. And so on. Same thing with the second derivative, sorry. All right. Now, the real trick here, unlike in the second order, is really finding the roots. You have the quadratic formula. So for polynomials of degree 2, well, it's easy. Polynomials of degree 1 are trivial. If it's affine linear, you can easily solve it, right? It's basically solved already. But quadratic, okay, you have the quadratic formula. That's fairly easy. There are formulas for degrees 3 and 4. They're kind of complicated. Nobody ever remembers them. Or, well, maybe there are some weird people that memorize them. But there are formulas. You can sort of plug into a formula, and it's gonna give you some very complicated, complicated looking solution in terms of roots and so on, right? But for degree 5 or higher, there is no formula. You cannot, there's no formula in terms of the roots and algebraic operations on the coefficients. So you can find them numerically, or it's hard. It's and it's basically impossible to really do in general complete exactly, right? It's we have lots of ways of doing it approximately. There's a lot of times it's good enough, but also in special cases, it's when the roots are kind of special, maybe there's a way of doing it. So for certain, for example, for certain fifth or sixth or whatever degree polynomials, there might be a nice formula. There might be a way to factor things. All right, but for an nth degree polynomial, there's always n roots, right? Well, some of them might be repeated, so you're going to have multiplicity, just like you can have a doubled root for a quadratic, right? That's if the quadratic is basically a square, right? And you can have complex roots, obviously, right? Just like for quadratic. But now you're going to have like combinations of these, right? And one usually uses a computer to find this, right? Sometimes you need to do it by hand, but generally in real life you'd use a computer to find these roots. But you could, if you see the thing, there's sometimes certain ones are easy to come up with. A lot of times 0 is really easy to figure out. Just can you factor out an r or r to some power? 1 and -1 are generally easy to figure out. I mean, you just basically plug in. That's all you're doing. You're plugging in different different r's and seeing what happens. So a good strategy is to start plugging in. Now, a lot of times, if you start plugging in and you get you plug in one number and then you plug in another number and you get you get a positive number, positive answer for one, a negative answer for that. Well, you don't have roots, but there would have to be a root in between, right? That's used in the when the computer is doing it often. If it finds two r's for which one for which the polynomial is positive, one for which the polynomial is negative, there has to be a root in between. Somewhere it had to go from positive to negative, so it had to cross the the axis, right? The x-axis. All right. Anyway, or the r-axis, actually, because if we're talking about the polynomial being polynomial in R. All right. So, for example, how did I figure out the one in the example? Actually, that's not quite right. The way I figured out, I went the other way around, right? I started with the answer and came up with the with the problem. But how could I figure it out? Let's suppose that if I had this polynomial. Well, okay, so 0 is not a root because if I plug in 0, there's this constant term, so I'm going to get 3 on the left-hand side, so it's not going to be 0. Okay, so 0 is not. So I could try 1 and -1, and if I try 1 and -1 in both times, I get 0, right? So that's good. So if we have that 1 and -1 are roots, we just need to figure out the last root. We know that there are, because it's a third degree polynomial, there must be 3 roots. So we know that there is another one. And we need 3 roots, right, to get the 3 solutions. So the third root is not hard to find. Right? If you found most of the roots, the last one is always not hard to find. Basically, so this guy is already monic, so there's no constant out here. So I know that that's just basic algebra, that if I knew the roots, I could factor it like this, right? I know that there is some factorization because the third root has to be real. So I know that I can factor it like this. So the constant term of this, I could expand this, but I could just figure out, well, what is the constant term? It would be this times this times this, meaning minus R1 times minus R2 times minus R3. That has to be this 3. Every other thing that I get from expanding this has an R in it, right? So that means that 3 is the product of the negatives of the roots, right? And I know 2 of the roots, right? I know 1 and -1, so I plug that in, and I get that -1 times minus R3 has to be equal to 3. That means that R3 is 3. And I have the third root, right? Okay. Now, what if I have, so that was, in that example, we had, I had 3 roots and they were all distinct. What happens if it's repeated k times, right? some number of times. Before, in the quadratic case, we could only have twice, right? So now, yeah, it could be repeated 3 times, 4 times, 5 times, however many roots you have, you could repeat, right? So in that case, so before we multiplied by x. So, well, what happens, you can also multiply by powers of x, right? So you start with the e to the rx, you definitely have that root. And then just like before, you add in, well, I know that e to the rx times x, and that's actually going to be linearly independent, right? Those two are going to be linearly independent. And then I could do with x squared and so on up to x to the k minus 1, right? So if I have, let's say it's repeated 3 times, I'm going to get e to the rx, x e to the rx, and x squared e to the rx. All right, so let's do an example. Let's suppose that I have this guy over here, and the characteristic equation is this guy, right? I can just, figure it out from looking at this. And by inspection, okay, again, you basically try different things. You notice that you can actually factor it out like this. You can definitely, factor out an r, and then the rest of it you sort of maybe notice that it looks like a third power of something. So you have like this 1 3 3 1, right? Well, with the negative signs, and so you just sort of notice, right? Again, you could use a formula. It is the whole thing is degree 4, but you could just divide by r and have a degree 3, and you could plug it into the third degree formula if you really knew the formula if you want it, or you plug it into a computer and it will give you this answer. Anyway, point is that the roots are 0, 1, 1, and 1, right? I have 4 roots. Well, one of them is repeated 3 times because of this third power over here, right? So the r equals 1, that root has multiplicity 3, and so the general solution is that I have e to the x. That's this guy, right? Then this guy is gonna give me this times e to the x, and then I have x squared times e to the x. So this part of the solution is coming from the r equals 1, right? Now the r equals 0, that just gives me a constant, right? Because r equals 0, e to the 0 times x is just a constant, right? This is 1. So I'm getting just C4 over here, right? So this is my general solution out here, right? And if I had initial condition, I should have 4 initial conditions. I should have the value of the function, the first derivative, second derivative, and the third derivative at a point, and I could solve for C1, C2, C3, and C4, right? All right. Now, we could also have complex roots, right? And complex roots, just like for quadratic, because we're starting with something real, they will all come in pairs like this. Some real part plus and minus some imaginary part. So whenever I have a complex root, I also have its conjugate, right? Now, if we have that, then if it's repeated k times, then the part of the solution that's corresponding to that repeated root, I could write like this. I'm again gonna get, just like for second order, I get e to the alpha x times cosine beta x, right? And the same thing with the sine. And then because it's repeated k times, I can also multiply by all the powers up to x to the k minus 1, right? Let's do an example. So suppose I have this guy over here. So the characteristic equation is, well, it's this guy over here. And I can, well, again, it's by inspection. I notice that I can factor it. Now, I'm not saying this is easy, but yeah, that's what it is. So it's this thing, this quadratic squared. Now, this quadratic, under the square, what I can do is I can complete the square, and I notice that it's r minus 1 squared plus 1, right? Which is going to be 0 whenever r minus 1 is I or minus I, meaning whenever r is 1 plus I or 1 minus I, right? So the roots are 1 plus I and 1 minus I, and I get them with multiplicity 2 because of this square, right? So really, there are 4 roots, right? 1 plus I, 1 minus I, then 1 plus I again, and 1 minus I again, right? I get each one twice. Well, this means that I have this this general solution, right? I get e to the x cosine x, e to the x sine x, and then I get, well, just a constant, and then also an x power, right? All right. So good. So so that's for high order. Most of the time, most things, most things end up being second order. High order does come up from time to time, but not that often. So it's not a huge problem. Then it becomes sort of more complicated to solve. But it's basically the same idea if you need to solve it. All right, so next time what we're going to do is we're going to look at some applications of the second order equations. Some real world or simple real world applications, but something that sort of shows off how these things work and why are the solutions what they are. All right, so that's what we're going to do next time. We're going to look at mechanical vibration, mass on a spring. All right, so see you then.